Themis is running the SAND lab at MIT in the mechanical engineering department, which stands for Stochastic Analysis and Nonlinear Dynamics. And he's involved in a lot of very, very interesting problems: extreme events, energy harvesting, closure models, reduced order descriptions of turbulent flows, dynamic orthogonal equations, of course, that he came up with a while back, finite size particle dynamics. It's a very wide and an extremely wide range of research topics. And today he's gonna talk to us about extreme events in fluid dynamics and water waves. So it's over to you, and thanks for giving a talk.
Thank you very much, Peter and Dimitri, for the invitation, and of course for the wonderful introduction. And it's a great pleasure to give this talk today. So this is the work that you're going to see is more or less the results of the last 7-8 years. It involves numerous people in my group, both postdocs and graduate students, and I will refer to them as we move forward. So the essence of the talk is on extreme events in fluid flows and water waves. And just to motivate a little bit, I'm coming from an ocean engineering background, and ocean engineering is one of the areas that involves a lot of extreme events. Here you see an offshore platform. These are multi-billion investments, and North Sea, huge water waves, right? This is a ship, actually it's a recording from the bridge. And you can see where the horizon is, right? Huge roll angles. And very important problems. And here you see the acceleration felt by an operator of this fast vehicle. We're talking accelerations that reach 6-8 Gs, right? And this is due to slamming events. And of course, we have other cases, flow separation and aerodynamics. All these problems can be put into the context of extreme events, in the sense that, you know, they are not happening every moment, but whenever they happen, they can be very catastrophic. And so it's important to be able to quantify them. And then, of course, we have extreme events involving fluid flows in scales much larger than engineering systems, right? This is actually a picture I took myself from New York City during 2012. There was a big hurricane that struck New York City at that time. And that caused flooding, right, throughout Manhattan. Actually was in terrible shape. And this is a rock wave, again, hitting a ship. So before I get into the actual analysis involving extreme events, I want to give an informal definition and, if you want, separation or distinction of extreme events from rare events, right? So extreme events, what is extreme events? They're large deviations from normality, okay? And on the other hand, we have rare events, which are typically low probability events. This can be, for example, winning the lottery, all right? This is a very low probability event. Of course, it's a very interesting event, but there is nothing other than, other than the fact that by definition, a specific combination of numbers gives you a lot of money, right? There's nothing other special about these numbers. On the other hand, extreme events, the way at least I see them in the work you're going to see later, is the result of the synergistic action between low probability events and dynamics. So there is a dynamical mechanism that can be triggered due to a rare event. This can be an instability, some sort of self-organized criticality, a feedback loop, right? So there is a special, the important thing for extreme events is that they are associated with interesting dynamics. They're not just random events. And to make things like more, how can I say, intuitive, I'm going to refer to this old game, the Monopoly. Monopoly is characterized by two things, right, in some sense. well, you have two dice that, that you use, and this is the source of randomness, but you also have rules, right? And one of these rules is that if you get the same numbers when you throw the dice, then you get to throw them again, actually. And if you do that, I mean, if you get again the same number, then you keep doing it. If you do it 3 times in a row, then you go to jail. So these rules is, if you want, the source of the instability. And if we run this very simple numerical experiment in MATLAB, then you see we have the core of the distribution, and this is associated with the 2 dice. But then we have a very long tail, and this is associated with the rules. But of course, these rules are being triggered from the source of uncertainty. So extreme events involve both dynamics and uncertainty. And there are known mechanisms of extreme events. People have studied them thoroughly in the past. We have systems involving slow-fast dynamics. Typically, there is a slow manifold, and then there are local instabilities, like you see here. And you know, if you find yourself close to these unstable islands, then you have jumps. This can also happen due to folding of the slow manifold. So in general, we have scale separation here. We have noise-induced instabilities, multiple equilibria, and then transition between multiple equilibria. These are triggered by noise. And then we have also homoclinic, heteroclinic cycles, like you see here. And again, these violent transitions between these. What we are going to see here is a more general perspective that involves a set. It can be an attracting set where the system lives most of the time. And this is typically high dimensional, right? You can think of it as the core of an attractor of a chaotic dynamical system. But it can be just a random set, right? The random phases in water waves, for example. So this is high dimensional. Typically, it has a very simple structure, for example, Gaussian statistics or uniform statistics. And then it is combined with islands of instabilities that occur in phase space. And what happens is that you wander around this region, this high dimensional region. And then if you find yourself close to these unstable islands, you undergo an extreme event, which has a signature to certain observables. So this is the picture we're going to use for what follows. We're going to focus on high dimensional systems. So just to motivate things further, in the context of water waves, what you see here is an airplane taking off from an aircraft carrier. And this is an old footage, but it's quite interesting. So you see the surrounding seas are not that bad, but then all of a sudden, completely disappears. Good news is that the airplane made it. Yep, it's right there. And the only thing that allowed it to survive is the fact that it used actual propellers, not jet engines. So a very popular model for this case is the modified nonlinear Schrödinger equation by Trulson. And well, if you want a very intuitive description of the mechanisms involving rock waves, in this case, essentially we have wave groups. For narrow band waves, we have wave groups. These wave groups, depending on their size and characteristics, they propagate with different velocities. And due to these different velocities, you have mixing essentially of wave groups with different characteristics. And some of these newly formed wave groups may undergo nonlinear instability, leading to an extreme event, like the one that you see here. So you can see that very clearly if you run Gaussian or linear simulation. This is the tail. If you run second order theory, this is the tail, and simulations using the MNLS. gives you a much more pronounced tail for the case again of narrow banded waves. In low Reynolds flows, this is the Kolmogorov flow for low Reynolds number. You still see interesting events. This is the dissipation over time. And I will play it from the beginning. It fluctuates most of the time around 0.1, but then there are certain cases where without any obvious warning, it undergoes very large values. So you can see the probability density function of this, and you can see again the very pronounced tail um, that extends, to very large values of the dissipation, although most of the time is around 0.1, right? You want to get a more dynamical perspective of what is happening. This is the statistical mean, this is the laminar solution, and then there is a stable submanifold here and an attractor around which the solution wanders most of the time, but then there are these sudden transitions crossing the donut across that create this sort of thing. Of course, it took a while for us to understand this sort of mechanism. And again, the idea is, what can we say about these extreme events? Can we predict them? Can we quantify their probability efficiently? So I'm going to focus on two problems related to extreme events. The first one is the prediction problem, and this is associated with finding appropriate observables that one should keep track in order to maximize the probability for successful forecast of extreme events. In other words, what modes or what degrees of freedom should one keep looking at in order to obtain information about an upcoming extreme event? And this is obviously important for decision making and control, but also for theoretical reasons, it's good to know what is the trigger of an extreme event. On the other hand, we are interested in the statistical quantification problem. This is more important for design and operation and optimization. And this is the probability of extreme events for certain observables over long time periods, right? So this is SIP motions that you see on the right. We have random Cs, and people are interested to quantify the probability density function of vertical bending moments, for example, or large pitch or roll angles. This is very essential for operation and design of these systems. So we're going to focus on these two problems. We will start with the prediction problem. And I want to set some motivation using a dispersive wave model of turbulence. This was introduced by Maida McLaughlin and Tabak in the 90s. It has essentially the structure of a nonlinear Schrödinger equation. You see, this is a nonlinear Schrödinger nonlinearity. But instead of having a Laplacian, it has this term here, the pseudo differential operator, where A is 1/2. And it tries to mimic the dispersion relation of deep water waves. We also have this dissipation term. This is selective dissipation term. Essentially, it's a damping term that kills very, very high frequencies that exceed a certain threshold, KD, right? High wave numbers in particular. So if we run a realization, you see we have these sort of things here, a very stochastic background, and then out of nowhere, you have these huge spikes forming, right, randomly. If we run the statistics for that system, you basically can see the Gaussian core in the middle, and then these heavy tails forming left and right, all right? And again, our goal is how to formulate good predictors for these events. So this is a system we had started working on in 2012, 8 years ago. At that time, we were going primarily intuitively to identify precursors. So we realized, I mean, it's, I think, an obvious observation that these sort of extremes, they must be associated with concentration of energy over a specific location. You have dispersion, you have deep water waves dispersion relation here. So, and in order to measure this sort of localization of energy, we use this Gabor type of function. It's essentially the projection of the wave field into a Gaussian of a given length scale psi, okay? We did this, we tried this for several different values of psi, and we realized that there is an optimal scale of psi that gives you very, very good prediction skill. So in what sense? What you see here, it's the conditional probability density function. On the left is on the vertical axis is the value of the precursor, and on the horizontal axis is the value of the observable of interest T prediction times ahead, all right? So you see that if we have very small value of the precursor, all the expected values are concentrated in this area. And then if this precursor exceeds a certain threshold, then immediately all the probability moves much further to the right, okay? So this is the correct prediction. This is false negatives. And the reason I'm showing this is just to motivate you and show you a situation of a good predictor. A good predictor is a quantity, or if you want a functional, that can parameterize effectively the region or all the possible outcomes of your observable. If you had a predictor, or what is a bad predictor? A bad predictor is something that where all the cloud is just, you know, in one axis, in the vertical axis or in the horizontal axis. In this case, it's insensitive on what is going to happen. So this turned out to be a good predictor. And it turned out that the scale that does that is the optimal scale is the dissipation scale. Okay, we analyzed this with a former postdoc, Will Cousins, in this paper. And as I said, in this case, the predictor was more of an empirical way to identify it. So we wanted to extend this sort of capability in more general systems described by a general state U, right? Some governing equations. Keep in mind, like we have Navier-Stokes in mind. KU is the divergence-free condition, initial condition, and this is the observable, right? And what is our goal is to identify initial states that trigger extreme events. People have worked a lot on this area. There is, as you know, large deviations theory that is focusing on understanding states associated with extremes. And for large deviations, what is the idea? The main idea is you set up a maximum value for the observable, right? Some value. This is your observable I. You say, this is the value I'm interested in. And then the next step is to check among all the states to find the one that has the maximum probability, assuming Gaussian statistics. So basically what you have to do is to find all the initial states that take you, or that lead you to an observable that reaches this maximum value, J naught, and among all the states, you have to identify the most probable one by making a Gaussian approximation of the attractor. This is, if you want, a very intuitive way to understand large deviation theory. Of course, there are certain problems with it. It works well when the underlying attractor has a Gaussian core, which of course is not always the case, as you saw with the donut. This is not the case, the Kolmogorov law. But of course, this can be fixed if we do appropriate things. The most important problem is that you have to search the whole space of initial conditions in order to characterize states with a certain growth rate, right, J naught. So it's good if, as long as your background space is low dimensional. To overcome this problem, we took a different approach. We, instead of looking into the full space, we focused on identifying the initial conditions that lead to certain growth of the observable over finite time horizon, but we searched over a certain high probability sphere, right? So we impose what we call feasibility constraint. So the feasibility constraint that you see here It's basically a set of initial conditions that a priori we know they have high probability. Intuitively, what is that? This is the set of initial conditions that live close to the core of the attractor. And the good news is that you can characterize that with low order statistics. You run a turbulent flow, you compute second order spectrum, for example. That gives you a hyperellipsoid where your system will live most of the time. So you optimize your growth rate within this high probability set. Of course, the Gaussian assumption is not essential. We don't rely on it. We just look for a high probability set. And most importantly, we don't search the whole space, but only the states that have meaningful probability. And it can be combined with standard reduction methods. We have shown, this is joint work with Mohammad Farazman, that this is a well-posed problem, and in fact, it behaves also very well numerically. And what it really does, like the mechanics of this idea, is that it looks for initial states that have high growth, but it excludes the completely exotic ones, right? The ones that may actually have really high growth, but have zero probability of occurring simply because they are not close to the core of the attractor. On the other hand, we are not looking for specific transient directions of high growth associated with a specific point, let's say the laminar flow, right? This has been studied thoroughly, as you know, in the context of transitional turbulence. You go around the laminar state, you perturbed over a very small sphere, and then you see which direction is the highest growth. Here, we are not constraining ourselves around the laminar state. In fact, we don't even assume a laminar state. We just want to find the highest finite time growth over a high probability set. So let's first see how that works for wave groups. We're looking for wave groups in the context of modified nonlinear Schrödinger equation with the most intense growth. We characterize wave groups with a very simple, if you want, two-dimensional model. This is the ansatz we use. A is time-dependent amplitude. L is a time-dependent length scale of the wave group. We plug in this into the modified nonlinear Schrödinger equation. We get this nonlinear equation that gives us the map that you see here. You don't even need to do that. You could, in principle, run, the direct modified nonlinear Schrödinger equation with a bunch of initial states, right, or initial amplitudes. But here we use the reduced order model that you see here. So what this map shows is for different initial amplitudes and different initial length scales of your wave group, what is the maximum amplitude over time normalized by the initial amplitude. And you see that the dark blue is essentially regions where you have no amplification of the initial amplitude. Basically, the wave group diffuses, or it gets larger length but lower amplitude. But then you also have these regions here, the colored regions, where you have your wave group essentially intensifies. Now, the question is, okay, as you can see here, the larger the wave group in terms of length, the more intense its amplitude is going to be. So remember, we're looking for precursors. So one could say, okay, then let's take a precursor or try to see what is the energy concentration over a large length scale wave group. Is this the answer? Well, in reality, no, because yes, you have these wave groups here in the dark red region. You see very large length and moderate amplitude. The question is, can you ever get this kind of wave groups as initial state? And the answer is no. We take a typical spectrum from water waves. We apply a scale selection algorithm. We generate several random realizations of this spectrum, and we see what statistics we get for the amplitude and length due to wave groups that are propagating under linear dynamics, if you want, right? Just the dispersion relation. And you see, this is the typical set of wave groups that one can find under linear dynamics. We take a contour of this probability, and this is what the feasibility constraint is. And we have to superimpose that with the instability analysis I just described below. I mean, above. You see that the very wave groups that lead to very large amplitudes are basically unrealistic. So if you want to combine probability and dynamics, you end up with a critical length scale that is both probable to occur, and if it occurs, it leads to a rogue wave. So using this analysis, we end up with this functional that is Gaussian, convoluted with the current state of the wave field. And this is the prediction map, right? And you see how nicely, again, it parameterizes the possible outcomes. And in the movie that you're about to see, I have colored, using this precursor and without solving any equations, I colored each wave group according to the probability given by this precursor to get a rock wave, all right? So you see that green is low probability, yellow is moderate, and red is high. You see that things are evolving happily. No, if you want, danger at this point for a rock wave. And then this is periodic boundary conditions, by the way. And then you see we have a wave that has formed right now. And according to the analysis, we have high probability for a rock wave in the future. And at this point, as you're about to see, we are very certain that this wave group, which otherwise in the I norm at least doesn't look that different from the rest, we are certain that this wave group will give an extreme event in the near future. And running forward, sure enough, we have a rock wave forming out of this. Okay. So we have applied this analysis on experimental data. This is joint work with Professor Chapchub and Professor Honorato. They gave us their experimental data, and we were able indeed to see that before the wave groups are becoming very big, we were able to observe or identify the critical wave groups in irregular C-state. Applications to Navier-Stokes, in this case, the Kolmogorov flow. The quantity of interest is the dissipation function. The Kolmogorov flow is basically defined in a periodic box, two-dimensional, and we are forcing with one wave, a single wave number. Perform the analysis, and we find these modes of vorticity. This is for different Reynolds number. J is the value of the optimization functional. And in this case, you can see how the critical mode, or the mode that is associated with the most important growth, is behaving. And this is again a demonstration. On the top left, you see the value of the predictor. On the bottom left, you see the actual dissipation. So at this point, we have prediction of an extreme event, as you can see here. And sure enough, right after, we have the extreme event forming. We have pretty good statistics in terms of the rate of successful prediction or rate of successful rejection. The prediction time, you see the eddy turnover time here is 0.5 almost, and the prediction time is more or less double than that. This is a challenge, like how to increase that, because if you increase it, of course, these ratios will go down. You will not have, equally good quality. And this is a problem we are still working on, and I can tell you a few things towards the end, how we could increase the prediction horizon. This is another idea. We work with Mohammed Farazmand on essentially controlling just a single mode out of all the many ones that this flow is characterized. And if you control the trigger, you can basically get rid of the extreme events. So this is a situation here. We have controlled the trigger, and that is sufficient to suppress the tail. This is the probability density function with and without control of the trigger. And you see that although the spectrum is more or less the same, especially for the basic wave numbers, you suppress the tail significantly by minimally controlling the trigger. Then a final thing regarding short-term prediction before I go to the other problem is bursts of dissipation in turbulent channel flow. We adopt we consider the minimal flow unit by Jimenez and Moine. In this turbulent channel flow, you typically have turbulence, as you can see here, and then very suddenly you have the flow becoming almost laminar, and then right after that you have an explosion of kinetic energy, and then of course dissipation and production of turbulence. So this is joint work with Dr. Blonigand and Mohammed. We did 2 years ago. We applied again the same framework. We obtained states with the strongest finite time growth. So we are using an adjoint solver, and the optimization constraint, or the feasibility constraint in this case, is defined by the first 30 POD modes. We are looking into this hyperellipsoid, if you want. You see different modes in this case. The optimal initial state for extreme growth over a finite time horizon is looking like this. This is the velocity deficit, and it's actually consistent with observations obtained by Jimenez and Pinelli. What Jimenez and Pinelli did, they tried to control different regions of the flow and see whether these suppress the formation of these extreme events, of extreme dissipation events preceded by extreme laminarization events. And they basically found that the region is exactly what we found later, through these extreme initial states. So this is again a demonstration of the idea. You see the flow on the right. Blue is the kinetic energy of the flow. Red is the predictor. And the predictor is based on the mode I just mentioned. And as we move forward here, we have very high probability, over 75% for an extreme event. And this is the case. You see the flow, it starts laminarizing. We'll turn it back just to see how things look at the moment we do the prediction. So this is how things look here. And then this is the point where the flow laminarizes completely. And of course, right after that, we have an explosion of turbulent kinetic energy. Again, the statistics are satisfactory as long as the prediction time is reasonable chosen. This is 3 times the turnover time. And this is what we have for the case of predictions. As I said, like, an important challenge here is how to increase the prediction horizon. Of course, we have to be realistic. This is a chaotic, these are chaotic systems with many positive Lyapunov exponents. So we have to be realistic on our expectations. But you see that choosing the right precursor is extremely important in any case. The second problem I want to discuss is involving the statistical quantification. And it's different in the sense that we're not interested for short-time behavior, we're more interested for the long-time statistics. So here we have formulated an optimal sampling approach. So what is the challenge for this kind of problems? We have very high dimensional spaces typically, and but the most important is not that. Even for low dimensional spaces, these are very expensive problems to run. You cannot run them, you know, hundreds of millions of times or even millions of times. You have an offshore platform and you do CFD modeling or a SIP and you do CFD modeling of it. You can probably afford a few hundred hours of simulations, you know, physical time. These typically corresponds to many thousands of hours in computational time. So now imagine you have an offshore platform, as I said, you can simulate it over a severe spectrum, C spectrum for like 1,000 hours. And now you want to find probabilities involving events that happen once every 20 or 30 years, right? So if 1,000 hours takes 1 month of computational time, if you want to do 20 years or 30 years, it's out of the question, obviously. So you have to do something different. And when I say different, you know, Markov chain Monte Carlo is a nice approach, but again, it's a randomized approach. It's not going to help you a lot. It may drop the hours by a factor of 10, but this is not enough. You want more than that. So having this type of constraints in mind, and whatever I'm going to tell you or present involves expensive systems to simulate. If you have like a system that is like a dice, just simulated for 1 million times, and that's it. So we are considering a dynamical system that is very high dimensional in the sense that it's very expensive to compute. And we want to estimate the PDF of a generic observable. Let's call it G. Theta, you see, is the source of randomness, is the random parameter space. And what we basically want to find is to characterize this quantity Q that is a map from the random variable space, theta, through this map T, which we have for any theta we like, but it's very expensive. We don't want to compute T many, many times. We want to compute T as little as possible, as few times as possible. So the probability density function for theta, the input parameters, is of course given, and we want to find the probability density function for Q. An obvious approach is to simulate the system for the most probable values of theta. But of course, this does not guarantee anything because probable thetas are not necessarily the ones that give you the larger value of t. On the other hand, even if you knew what thetas give you the largest value of t, this is not the answer either, because these thetas may be completely exotic again, without any probability. So you need something in the middle. You need thetas that are both probable in a realistic sense, but they also, involve large outcomes for t, although you don't know t a priori. So we will do that with a new, if you want, type of active learning approach. And our goal is to minimize the number of experiments for accurate estimation of the output PDF. What is the idea? We are given n-1 experiments, meaning the outcomes for n-1, theta 1, theta 2, theta n-1. And we want to optimize theta n for efficient estimation of the output PDF. The way we do it is that we set up a Gaussian process regression scheme that provides us the mean estimate for theta and for the uncertainty of this estimate of theta. This is based on the n-1 previous experiments. And then we formulate a sequence of PDFs based on the surrogate model. So you have the surrogate model produced by Tn-1, the best estimate, using the Gaussian process regression. You have the statistics of theta, so you can get the statistics of T bar, right? This is f of T bar. So this is your map, right, T. And these are the values that you already have, and it allows you to build a surrogate. Okay, Tn minus 1. Is this enough to choose the next experiment? Well, not really. The way we do it is that we formulate two critical boundaries, if you want. This is the worst case scenario in the positive sense. So this is Tn minus 1 plus 1 standard deviation, and this is Tn minus 1 minus 1 standard deviation. If you have sample enough over your theta space, so this error goes down, these curves will be on top of each other, meaning the dashed curves and the blue curve, and you will not need anything more, right? So we add a hypothetical new point theta star, and when we do that, of course, the blue curve does not change because we don't know what is the real outcome. So we hypothesize that the outcome of this new theta star is given by the best estimate we have. But what changes when you add this hypothetical theta star is the boundaries, okay, the uncertainty boundaries here. Based on that, we obtain these two additional sequences of PDFs based on the confidence intervals. These are the PDFs of the map plus and minus 1 standard deviation. And we formulate the problem like this. We are interested to find the theta star that will minimize the L1 difference between the logarithm of the PDF of the map plus 1 standard deviation minus the logarithm of the PDF of the map minus 1 standard deviation. So why we chose this particular functional between PDFs? We could have chosen any standard functional like the KL divergence, right, between PDFs, or even the L1 between the two PDFs. Well, there is an important reason. We have the L1 of the logarithms because we want to emphasize the tails. And this is not sufficiently emphasized if you multiply with the probability density function itself, in which case you recover the KL divergence. So we remove this term, meaning the extra PDF multiplication, and we focus on the L1 difference of the logarithms. Of course, we do not need to accurately know the parameter to observation map in order to compute that. It's given by the surrogate. And the sampling, the most important point about this process is that the sampling, the particular theta star, it depends directly on the observable we are interested to characterize. So different observables will lead to different thetas, to different optimal thetas. If you want in an offshore platform to, for example, observe the stresses, you may need, I mean, the vertical bending moment, for example, you may need different wave groups to simulate compared with the case where you're interested to model, let's say, the heave, okay, of the structure. So the selection of theta n, the new sample, does not depend on the actual value of the map. We have a consistency theorem that this is converging to the real distribution as the number of samples, of course, converges to infinity. We have analyzed the behavior. This is with a former student of mine, Dr. Mohammed Mustafa. We have analyzed the asymptotic behavior of the selection criterion. And it turns out that it has some really nice properties. Asymptotically, it looks like this. It's the average of the error of the Gaussian process regression, but normalized by the probability density function of the output. Now, what this says is basically that regions with very low probability will get promoted in the sampling process. So extreme events are not left behind. Rare events are basically counting as much as regular events because of the term, the denominator. If we had KL divergence, then we would have this term that you see the denominator appearing also in the numerator. And that will give us just an uncertainty sampling based process, integrated uncertainty sampling. So this is why it's very important not to include the probability density function in the optimization function. So this was in 2018. We ran several things with that, and we saw really good performance. The downside of this thing, if you want, the disadvantage is that it leads to a very expensive optimization problem. This was later solved in the 2020. Is a recent paper in the Proceedings of the Royal Society, where we were able to derive an upper bound for this metric given by the quantity that you see on the right. And this is actually very intuitive. It's the weighted average of the error, sigma n square, times the probability density function of the input, and divided by the conditional probability density function of the output for a given theta. The good news with this criterion is that you can compute its gradient analytically, so you can couple it with gradient optimization algorithms. So a very quick summary of the sampling criteria that are available. We have criteria based on mutual information. We have criteria based on uncertainty sampling, and the criteria based on the integrated variance reduction. You see this is input weighted. And using the analysis I just presented, we have the likelihood weighted version of the uncertainty sampling that you see here. This is a new criteria, and the integrated variance reduction, likelihood weighted version of it, which is exactly what I have, what we started from and got through the PNAS paper I mentioned before. So let's see how things work, right? I'm considering a very simple problem. This is a nonlinear oscillator excited by color noise. We do a coherent live expansion of the color noise, and we keep 3 terms, Gaussian statistics for the coefficients. The f function is a nonlinear function that is chosen in a way so that we get interesting tails. And so the probability density function of the output, or if you want the target PDF, is what you see here. For a 2-dimensional truncation of the input, the map, the output map that we don't have available, but we can get at any point, is what you see here. So we start with 4 initial points, and after 4 iterations, this is how the PDF looks like. The red is the prediction, the blue is the exact. We continue, we proceed, and as we increase the number of iterations, you see how we have convergence. So this is with a relatively order of 100, a relatively small number of iterations, but yet you see how nicely we recover the tail. The dashed line, the gray line, is 1 standard deviation. So we're able to recover the tail several 8 to 9 standard deviations away from the mean. But you also see how the samples are chosen, right? The PDF of the input is concentrated in the center, but yet the algorithm is able to understand that extreme events are basically living here and here. So we're able to recover these things. Application to a 3-dimensional problem, we get again, this is with 100 iterations, this is with 200 iterations, and you get the tail in different cases. This is how the logarithm, this is a very tough criterion here. We compare the L1 difference between the logarithms of the approximated PDF and the target PDF, and you see how nicely it converges. It's shown in logarithmic scale, although it's different of logarithms. And this is again the Q criterion. This is comparison with the other criteria I mentioned. The blue lines are the non-weighted criteria with the output. The solid lines are the new criteria, the likelihood weighted criteria I just presented. And again, E of n is the difference of the logarithms of the target PDF and the approximated PDF. And you see the difference. This is in the presence of noise on the right for the observations, and on the left is 0 noise. So it makes even more difference if you have noise on your observations. And it significantly improves the convergence of the scheme. We have applied this in a more realistic scenario of an offshore platform that is subjected to random water waves. For the waves, we are using an SPH code to characterize the loads. This is expensive, of course. For the waves, we parameterize them with wave group size and wave group length. That gives us a map, the amplitude and length scale, θ1 and θ2. As I mentioned, this is an expensive simulation to perform. A single wave group simulation with order of 100 seconds take approximately 22 hours on a modern GPU. This is just to show you how things, like how such a simulation looks like. Right, and this is the results now. We start with the initial distribution, 4 Latin hypercube samples. This is the initialization. We use the L2 metric for, at the beginning, just to characterize the core. And this gives us 4 samples. And then we use the L2 of the logs. And you see how the PDF looks like. This is for the force in the X direction. After just 15 iterations, right? We just run 15 wave groups and we're able to recover up to 3 sigmas, the tail of the PDF. And this is again the corresponding results for the moments in the Y direction. We have very big computational cost. This is the convergence analysis with respect to sampling, with respect to the input of theta. Yellow is Latin hypercube, red is the proposed idea. We have applied this in other systems, including extreme ship motions and loads. This is a collaboration with Carderock, the Naval Sea Surface Warfare Center. We use their codes to characterize the motion and perform adaptive sequential sampling to characterize extreme event statistics. This is work of Ken Stevens, a graduate student at MIT. And you can see the midship bending moment. This is the Monte Carlo based on 10 to the 4 hours. And it is compared with the adaptive sampling that is using only 20 samples to recover the tail shape. So some future directions that are interesting to pursue. We want to formulate precursors as a Bayesian optimization problem. And we want to do that in order to increase the prediction horizon. We have seen what is the limitations, or what are the limits, if you want, of the approach I presented before. And we have initial evidence that formulating the problem in a Bayesian setting significantly increases the prediction horizon. We want to apply optimal sequential sampling for higher dimensional problems. This is a challenge because Gaussian process regression behaves okay for order 10, 20, 30 parameters. If you go to hundreds or thousands of parameters, you have to utilize other ideas. One of them that we are exploring is sparse Bayesian regression. We're exploring applications to optimal training of Bayesian neural networks. Here the problem is reversed, right? So far I've been telling you what samples should I use to characterize extreme events. Now it's opposite. I have a map that I want to characterize, and I want to do that with a minimum number of samples. So we're talking about optimal training of Bayesian neural networks, or optimal choice of training data, if you want, if you don't have plentiful data. And then from a more fluid dynamics perspective, I'm thinking a lot on understanding precursors or triggers for sporadic inception of spatially localized patches or spots of turbulence in transitional boundary layers. So with this, I would like to summarize very briefly. We have been talking about tracking the precursor. I've presented an optimization method that identifies precursors of extreme events. And it gives us hope that we can predict accurately the occurrence of extreme events. But of course, there is work to do in terms of increasing the prediction horizon. And then the statistical quantification problem, where again, the smart data is actually more advantageous than big data, simply because you don't have big data in many problems of interest. And we have shown that indeed it can accelerate convergence if you carefully select your samples. You have to pay the overhead on solving this optimization problem, but for expensive problems is worth it. So with that, I would like to thank you for your attention. I'm happy to take any questions.
Great. Thank you very much, Themis, for that very nice talk. So I open the floor to some questions from the audience. So I think the best thing is just to unmute yourself and ask a question if you have one. Maybe while people still think about it, let me start. In order to predict these rare events, have you actually played with techniques like time delay embedding, a little bit like Ruel and Takens, to actually get a better predictability of these rare events? Or is this something that just doesn't work for rare events?
Let me tell you, excellent question. We have actually done work, and it was published 2 years ago in PLOS, where we used exactly this idea of LSTMs coupled with reduced order models, just simple Galerkin projected reduced order models, with the idea being to predict extreme events. It relies heavily on what modes you choose. If the modes that you choose do not include the precursor mode, then you're not going to get the extreme events. The problem is that you cannot apply LSTM for thousands of modes or hundreds of modes.
Mm-hmm.
So you find an obstacle there, right? If you know what the modes are, then yes, you do LSTM on those and you're happy. But the challenge is, what are the modes that are the ones that are relevant? And it's not necessarily the high energy modes, of course.
Yeah, of course. Yeah. All right. Any question from the audience? Please just chime in.
Okay, Peter, may
Oh
I
yeah,
ask a
Shusong,
question?
please.
Okay. Kind of tutorial question at the tutorial level, really. So there are extreme events, okay, kind of involving some random, kind of external random noise, so to speak. But there are also those events which kind of fairly deterministic, like the intermittent turbulence, right? Like in channel flows, it seems there's no persistent kind of, apart from computational error, but there's no kind of random forcing. So, so are your method equally applicable to that, characterizing this or predicting this? And
So
even among the in the case of randomness, you may have additive noise and multiplicative. So your methodology is based on kind of, it seems to me, and we assume some additive noise.
So
There
all the
are also
problems,
multiplicative.
yeah, the problem for all the problems I presented, there is no noise, okay, at all. All the extreme events you saw, they are caused simply by intrinsic instabilities, by chaotic dynamics. Now, if we are talking so in other words, the method is, if you want, formulated for deterministic systems. Now, for the case where you have noise phenomena, as long as the extreme events you observe are driven by intrinsic dynamics, then the framework will work. If they are driven by extreme forcing events caused by the external noise, this is not going to work, in the sense that there's no instability to capture there or to trigger to identify.
You had a very simple example, like oscillator with a random forcing, right? So I thought
yeah.
that's the one is the rare event is associated with fortune, right? Otherwise, the oscillator wouldn't have nothing either.
Exactly.
I don't know, the nonlinearity. Of course, there is nonlinearity. You may have homoclinic. But
Exactly.
are you saying
Yes.
if you take off the random forcing away, you can, there's all kind of intriguing.
Yeah, as I said, the understanding or the assumption is that the extreme events that you observe, they are caused by some nonlinear dynamics and not necessarily by the additive noise.
Yeah. Associate. Yeah, I really, kind of like this idea. I can see, at the other extreme of the spectrum of this approach, there are completely linear dynamics explaining log waves, and I never understood at all about those, because there is no mechanism there, to amplify certain factors. But here, I do see this, not. But combining these statistics and the deterministic aspects is quite it's interesting, but there are a lot of details to be understood. Yeah.
All right. I think we have Davide from East Anglia raised his hand. If you want to unmute yourself and ask your question, please go ahead.
Yeah, thank you. Thank you, Themis, for this really nice talk. I have actually two questions, really quick question. So the first one, maybe I missed it, but can you confirm that you said that your optimal sampling strategy is a convergent method, if you prove that? And
it's
then okay, so I was just wondering, does it work also for models which are integrable? For example, just a normal Schrodinger equation. Does it work for that, or there are some constraints on the model?
No, no constraints at all. In fact, let me go back to the. In fact, there are we don't assume a model. We assume that there is a well-defined map from the parameter. So you assume that there is some sort of map from the random parameter space to your output, with the possibility of some noise, right? Observational noise. You don't have to assume something about T other than some basic smoothness conditions, right? So if T has jumps or these kind of things, then you have to be careful with your Gaussian process regression, because it will not be a good approximation. But there are no assumptions for the dynamics.
Okay, so even if you have, I don't know, infinite number of conserved quantities in the system, it doesn't matter. You can still do this. That's pretty amazing. Yeah.
Can I also ask one on the optimal sampling strategy? It seems like this is a sequential algorithm, right? So you have the n-1 and then you go for the n. Can you actually use that in a combinatorial way, very much in the spirit of leave one out, where you actually go back to the parts? You can pick any n-1, not the first n-1, but leave one out and then revisit that one.
This is a great question. I mean, for at least the problems that I have worked on, as long as you have done the n-1 experiments, if I understand the question correctly, I don't see the point of leaving them out, except like if you have them already, even if it's not very informative, you just include it. Like it will not harm you.
But yeah, no, not leaving one out, but just you assume the n-1 that you have, and then you go for the n. But
I see.
And leave the first one out, and then leave the second one out, leave the third one out, and so on and so on.
Yeah. I mean, I've not thought about it, but it's an interesting direction, for sure.
Yeah, this is sort of a cheap way of with response surfaces to get error bars by assuming all the other n-1 are exact, and then you try to reproduce the one you left out.
I think this is, I see what you're saying, Peter. Yeah. This is, I think it will, in my view, I think it will work simply because the core of what I presented is essentially to give emphasis to the output. The way we do it with the new criterion, people have been doing sequential experimental design, of course, before this work, right? It's a big field. They have been using a lot mutual information to do that. And mutual information has certain downsides. You know, it's not working well for high dimensional parameters, etc.
Yeah.
You can apply all the ideas that people have been using previously, but with this additional twist of changing your optimization function so that you give extra emphasis to the output. We've seen that, especially in the context of extreme events, this is really important because you don't just care to fill out the input space when you sample, but you care for the pieces of the regions of your input space that contribute to the output.
That contribute to the output space. It's a little bit like balancing, right? It has something that takes something that is controllable to something that is observable.
Exactly.
Okay, we have another hand up, Ioannis.
Hi, Themis. Thanks for the very nice talk. That was really interesting. I have a quick question, perhaps, on the prediction of extremes or of rogue waves. I'm wondering whether you've so using the MNLS has an inherent narrow-banded assumption. Have you looked at perhaps extending these to more realistic broad-banded waves? And have you thought about maybe wave breaking or incorporating that into the prediction system?
All right. Yeah, great question. Okay, that opens this is. I'll try to keep it short. MNLS is one model and describes, if you want, a very specific mechanism for getting rogue waves. And those of you who are working in rogue waves, there is a huge debate between two communities, essentially, those who suggest, rightfully so, that for broadband seas, it's not the MNLS a good model to capture rogue waves. So if we're talking about rogue waves that are created in a broadband situation because of superposition, random superposition, this is, of course, a situation that is not associated with an inherent instability, right? It's a purely random case, and the statistics are very Gaussian or close to Gaussian in this case, and you have nonlinearity because of subharmonics, etc. This is not a case where you will be able to get a good precursor. If, however, even in that case, there is important, non-negligible probability to get rogue waves because of Benjamin Fair instability, this is a case where this framework will be able to capture. So that was the first thing I wanted to mention to your question. There was a second part that I forgot, but yeah, this is very short, the answer.
Yeah. But of course, you can have a broad-body system where you've got rapid non-linear dynamic exchange of energy that would effectively lead to rogue waves instead of jumping through a very well-defined group structure. They jump out of more broad-body. So it's effectively both superposition plus non-linear dynamics.
Yes, but the case is that if you have, in this case, the nonlinear dynamics do not amplify the wave group, it might be 5–10% amplification. Like the big thing is coming because of the superposition. So you will not get a severe amplification because of second order effects. This is the difference. So you will have nonlinearity, but this nonlinearity, it's not going to do the same thing as Benjamin Fair instability.
Good. We have a hand up from George.
Yeah, Themistocles, very, very, very interesting presentation. What I want to ask you is this: have you tried to see what happens with CLVs, covariant Lyapunov vectors, when extreme events are happening? Is there some kind of alignment of these unstable CLVs that lead to this thing? Have you looked at this?
Yes, we've seen that. So, excellent question. Okay, here's the challenge with using CLVs. These things are transient effects, but they coexist with persistent instabilities. So it's not like whenever an extreme event is happening is the only unstable thing that is happening. There are instabilities that go on and continue to be there. it is true that the moment an extreme event is happening, at least for the systems we have studied, the maximum finite time Lyapunov exponent is, and the corresponding Lyapunov vector is aligning with the direction of the instability that leads to the problem. So, and we have used that even as a precursor. That was a physical review e-paper with Mohammed in 2015. I will tell you, the problem with that approach, it's not very practical because you cannot really compute CLVs on the fly to use them for precursor. If you have a magic box that can give you CLVs, then we can use that for precursors. But other than that, yeah, that's the short answer.
Okay. But there is a link there.
Absolutely. No, there is alignment. And it's interesting that, as I said, from all the modes that I've seen, like CLVs are the ones that can actually capture these transient instabilities. You just use, simple POD modes, like it's not, or Koopman modes, for example, they will not be able to see. Because, for example, Koopman modes, they will focus on the persistent instabilities, not the transient ones. So
yeah. Okay, thank you.
I'm going to squeeze in a really quick question. Have you actually tried to control turbulence, for example, in the minimal channel unit or so? It seems like this is perfectly set up for model predictive control that is event-driven.
We have not. This is a great direction. One of the reasons was very practical. Our collaborator, who at that time worked at NASA and provided all the infrastructure and the computational skills, he moved to a different job. So we had to wrap up the project. But
Patrick,
I look forward, to collaborations to do that. I believe also it's like a very interesting problem to consider.
Yeah, very good. All right, any more questions from the audience? I don't see any hands up, but this is your final chance to.
I would like to ask a question.
Yeah, Trevor.
Yes. What about the standing waves? There's a theory which says that the standing wave at maximum height has an angle of 90 degrees. This has become controversial, although there is experimental evidence in favor of Penny's result. Do you have any feeling about how this would fit into your picture?
I have, I think this is a very interesting question. We have not really got into the detail of the shape of the waves, primarily because we have been looking at the wave group level. The analysis for extreme events essentially assumes, based on the broadband, on the narrowband assumption, assumes wave groups. So all the analysis we have done is primarily focusing at the level of groups of waves rather than, the specific. But what I can tell you is that, at least for the rogue wave prediction, individual details of waves within the wave group are not that important or critical for the evolution of the wave group. So I don't know if that even partially answers your question, but yes, in this context of wave group analysis, they don't.
It did not really seem to fit into your picture of either extreme or rare. It's not rare or extreme, but it's certainly extreme in a way, but it's not rare in the sense it's periodic.
I see.
The wave goes up and down, so in a way it doesn't quite fit into your picture.
This is interesting. Like, I will look into that, and I'm happy to discuss more.
Yes, thank you.
Of course, thank you.
Good. All right. So we went quite far with the questions, which is a good sign. It was a very, very interesting talk. So I want to thank everybody for joining us for the Fluid seminar. And I want to especially thank Themis for this really, really interesting talk and taking the time out to give this presentation. So thanks a lot. It was very, very interesting.
My pleasure. Thank you very much for the invitation, Peter.